Hey everyone, I'm Sarah, and in this video we're going to finish the project that I've been putting off for 7 years. This is the final part in a series of videos. The work we're going to talk about here was done over several weeks, and I've had to shrink it way down to fit into one YouTube video. But even so, I suspect this will be the longest one in the series, so buckle up. Before we start, let's take a minute to review how we got here. We are in the panel switch, a telephone switching machine from the 1920s. It is the last of its kind in the entire world, and it switched telephone calls in Seattle from 1923 all the way up to 1974. It was brought to the museum in 1986, but when they did that, they only brought parts of the original machine, and they forgot a few things. One of the things they forgot was some of the hardware needed to make this frame run. This is called the sender test frame, and as you might guess from its name, this tests senders. Or at least it did 50 plus years ago. But 1974 was the last time it did anything useful, and I'd like to get it working again, because the senders really need to be tested. See, senders are like the brains of this machine. They listen to and register the numbers that you dial with your telephone. And they cause the selector rods to go up to build the connection for your call. Senders are really important, and without them, the whole machine doesn't do anything. Normally, when one of them breaks down, I have to test it by manually dialing a phone call and watching what the sender is doing. But with this fancy test frame, I can set up all kinds of tests and have them run automatically, which will help me detect problems earlier before they impact service and resolve them more quickly once they're found. The sender test frame is really complicated once you get into the details. But in order to help you understand what we're building here, I'm going to try to explain it to the extent that I can. In order to test the sender, this frame pretends to be a caller and dials a number into the sender. We can specify what number is dialed using these keys. As the number is dialed, the test frame checks that the sender has registered those digits correctly. Then the test frame pretends to be the rest of the panel switch and allows the sender to set up a call through it. The sender, under test, thinks it's setting up a real connection, but in reality, the test frame is providing input to the sender and is measuring how well it performs against that input. In order to test edge cases and error handling, we can again use these keys to tweak how the digits are dialed into the sender, and also to adjust the behavior that we expect from the sender. In order to provide that dialing and signaling simulation, we need special circuits that pretend to be a customer's dial, and also pretend to be a selector rod as it's moving up over the panel frames. These are the circuits that they never brought to the museum, and without them, the test frame just kind of sits there trying to dial, which will never happen. Both of these circuits are essentially low-speed oscillators that provide a square wave output. They use relays to oscillate tens of times per second, and those oscillations are fed into the sender test frame and then out to the sender at the correct times during the test process. The first oscillator circuit we already built was the easy one, and we got it working in a previous video in the series. But this time, we have to build the dial pulse oscillator that simulates the pulses coming from a customer's dial. This is substantially more difficult, and to be honest, I wasn't sure whether it would work or not. The dial pulse oscillator, or interrupter as it's called here, generates pulses with specific configurable make and break intervals, and at very particular speeds. These speeds and pulse intervals are designed to test the limits of the sender itself, and each particular combination tests a specific edge case inside the sender, pulse detection, and counting logic. So it's important that we get this right. So the EEs among you are probably asking questions. Couldn't I just do this with an Arduino and a relay, or a 555 and something else? Why would I go through all of this trouble to do the hardest possible thing when there are several easier, more modern options? Well, I have two answers for that. Number one is that in this museum, as much as possible, I like to keep things to their original spec. If I replace one circuit with a computer, why not just replace the whole machine with a computer? What's the point of having something old and real if there's just a computer hidden away inside making it go? The second reason, and I've mentioned this before, is that I don't enjoy working on computers or solid-state electronics of any kind. Like, I can do it, but I try as hard as I can to avoid it. So while this may seem like the worst possible path to some folks, I'm going to try and build this circuit for real by gathering all of the components and running each and every wire by hand. Okay, so let's look at a simplified schematic to understand how this thing works. Before we get into it, I need to mention that the keys shown here are replaced by relays in our circuit. But that doesn't impact this explanation. This schematic is from a newer switching system, so the implementation details differ, but the electrical concepts are exactly the same. Anyway, there are 4 main oscillating relays here, but we'll look at just 2 of them to start with, int and int1. These relays will create the square wave-shaped oscillations that our test circuit needs. The other 2 are just pulse repeaters. The pulsing relays are polar, which mean they can operate in either direction depending on the polarity of the current going through their windings. One polarity makes them operate to the left, or front contact, and the other polarity makes them operate to the right, or back contact. In addition, these particular relays each have 2 windings. The primary winding is used to bias the relays in the left direction, and the secondary is used to release the armature to the right against that bias. The int and int1 relays start in the left position because current is flowing in their primary windings in a direction that makes the armature move left. They also have secondary windings, which will become important in a moment, but for now, their secondaries can't do anything because of this shunt path here and this make contact here. When dialing is supposed to begin, the shunting ground is removed from the secondary winding of int, which causes current to flow through the secondary winding that opposes the current flowing in the primary. Soon, there's so much current flowing in the secondary winding that int releases and moves its armature to close a circuit on its right, or back contact. As current flows through the secondary, it charges these capacitors through these resistors. Eventually, the caps will completely charge, and current will stop flowing. Thus, the length of time that this relay stays released is dependent on the values of these resistors and caps, and this resistor in series with the primary winding. These values are controlled by keys or jacks on the test frame itself. Now that int is released, its contacts discharge a capacitor in series with the secondary winding of the int1 relay. By now, int's capacitor has charged fully, so int reoperates to its left or front contact. When this contact closes, int1's capacitor is allowed to recharge, which causes current to flow in its secondary, causing int1 to release, just like int did a moment ago. int1 will only stay released for a moment, but while it is, it discharges a capacitor in series with the secondary winding of int. Now, int1's capacitor is charged and current stops flowing through its secondary winding, causing it to reoperate. This cycle repeats indefinitely, each relay releasing as current flows through its winding and resistor capacitor network. And upon releasing, it discharges the circuit of the other relay, ensuring that on the next go-around, the cycle will repeat. The neat thing about this is that by precisely specifying the values of the capacitors and resistors, we can control the pulse speed and pulse width with impressive accuracy. These A relays here do just that. They operate based on the settings that I put into the test frame. And each one of them has contacts that close all of these different caps and resistors down here to get the exact values I need to wiggle int and int1. Building this is going to be a big deal. So before we get started, let's clean up the sender test frame. It hasn't run in 50 years, so it's a little crusty. First, the motor isn't working, so I'll just pull it out and replace it with a spare. Later, when I have some time, I'll put the original motor on the bench and rebuild it. Then, I'll clean off some of the scunge that's built up on the horizontal surfaces over the years. After that, I'll just plug in the motor fuses and look at that, it starts right up. Now that the test frame vertical shaft is spinning, it'll be much easier to clean off the drive discs for the sequence switches and get them looking shiny again. Oh, that reminds me, I should definitely check the oil in this gearbox. Looking at the sight glass, it seems nearly empty, so I'll add some up to the correct level. This is a low-speed gearbox, so running it without oil for a minute won't hurt it, but I definitely don't want to leave it like that in the long term. After a few minutes, we can see that the oil comes up to the appropriate point in the sight glass, so the frame is now safe to run for hours and hours at a time. Next, I'll tackle the sequence switches on the vertical shaft. They're almost certainly going to be cranky after staying still for all these years. So what I'm doing right now is just getting the sequence switches moving again. I anticipate that they're mostly fine, but there's probably a lot of oxidation on them. So I'm going to check them mechanically for sticking. So I'm applying a slight pressure here. And this tool, that tool is the sequence switch maker goer. And if I apply slight pressure, that one stops, so that one needs to be adjusted. Ooh, exciting. This is also loading down the motor and the gearbox a bit, so I don't actually mind that. That's pretty good. So with electromechanical circuits like this, you need to start with the mechanics, because none of this stuff is going to work electrically if it's not working mechanically first. So, like I said, this has been sitting for 50 years, so it's very, very likely, in fact, very probable that there is all sorts of oxidation and wear on these contacts that they have not moved in as long. So I just want to give them a chance to stretch their wings a bit. I'm squeezing this outer disc here. This is not conductive, this very last thing I'm touching. And I'm looking for the switches to stop. If they stop, I know that something's wrong. They shouldn't. They should be able to overpower a gentle squeeze from my hand. So that one's good. That one's good. That one's good. Yep. Good. And we're going to keep going all the way up to the top here. Now this top one isn't going to work because I got the oxid on the drive disc, so I'm going to need to fix that. Watch. Yeah, it's engaging, but it's just slipping because deoxid is very oily. Okay, let me get the sauce I need to clean this up. So we're going to use IPA for this. Really, you just want anything that'll cut through any oil. That's what we need to get rid of. And we just have to keep doing that. As the disc rotates, we just have to keep doing that until this paper towel is mostly clean. So you can see it's getting better as I go up. Okay, this is kind of a pumice stone, and it's in this holder, which is hollow, and it's got a cotton rag stuff behind it. And this is a cup of water. And what we're going to do is we're going to get this stone and rag and holder nice and saturated. We're going to fill up this whole thing with water. And then we're going to roughen up the surface of these discs by rubbing the pumice stone against them, like this. This serves two purposes. Number one, the stone material comes off on the disc, kind of makes it a little bit more, gives it a little bit more friction. Second purpose, because we're using water, is that it makes the outside of the disc rusty, which also increases friction. So we want these discs to be a little bit rusty. It's the only part of this machine that should be rusty. Now, it's not a horrible kind of rust that eats away the metal. It's just like sort of an oxide, iron oxide coating on the outside. And you could see it here. Take a look at the outside of that disc. That is rusty. And so is that. And I expect it to be that way. And that should be rusty, but I got deoxit all over it, which was my fault. Needs a little help from my hand, but that's because it's wet. Once it dries, it'll be good as new. Okay, so we leave it alone. With that done, let's look at the physical arrangement of my new circuit. Eric had already cut down the relay mounting plates for me, but now I had to do a little Tetris to figure out where all the parts for this circuit were actually going to live. If you remember from way back when I started this, I was missing some mounting plates, and others were far too wide to fit into the space that I had available. So I have to be extra careful during this step to ensure that each component has a place to go and that I'm not missing anything. It would be horrible to build this entire thing and then only then realize that I had missed something and I had to tack it on after the fact. So I took the schematics home with me and I spent an evening with them unfolded across my living room floor. Then, with an unholy amount of browser and editor tabs open, I calculated which version of this circuit we would actually need to build in the museum. See, these schematics show you every possible version of the circuit all flattened down, and it's up to you to know which options and wiring you need in order to make it actually work. I used a combination of the original records for our panel switch plus knowledge of the actual application of the circuit in the museum. I was then able to create a definitive list of what we needed, what we had, and what we were missing. With that list, I grabbed my big tub of parts and began to sort through it. I kept track of everything by creating a spreadsheet and marking off each component as I physically held it in my hand. Then, I spent a lot of time cross-referencing each component against the schematics to be sure that the thing I was holding in my hand was actually the correct object in the correct configuration. I also took several trips to our off-site storage to dig up the parts that I was missing. Our storage is not nearly as organized as I'd like, so sometimes this involved hours of digging through random boxes and hoping to stumble upon a gold mine. This part of the job was really nerve-wracking for me. I knew what I had to do, but at this point I had no idea if it would actually end up working or not. So I just had to keep blindly pushing forward on the faith that it would eventually all make sense in the end. The process of finding parts and organizing them actually took a week or two to complete. But once this was done, it was time again to get out the old plywood board and start laying out my circuit. It may seem like there's a ton of variability in the layouts that I could have chosen, but it really kind of built itself. There were only one or two choices that made sense in the end. Big pulsing relays on top, and then the land of chunky capacitors, followed by smaller control relays, then resistances, and finally the terminal strips at the bottom. Now here's the thing. There is no way that I'd actually be able to build this wire form by myself. Keeping track of each wire color, its source and destination, routing through the form, and keeping it neat and tidy, all while having some traceable list of what was done and what was not, was just beyond the ability of one Sarah. So I asked my friend Matt for help. Matt understands Bell System schematics and has a very keen sense of detail and orderliness, without which this just wouldn't have gotten done. So we split the job in half. Matt would read off the source and destination points and color of each wire, and then I would run it in the form as neatly as I could. As we completed a wire, Matt circled both ends on the drawing so we can keep track of where we were. In order to make this a little less daunting, I edited the schematics and printed off copies at our local Kinko's. It was expensive, but totally worth it to have just the stuff we cared about and be able to write and draw all over them. One of the most difficult parts of the circuit were those A relays. There are 7 of them, and if you remember, they cut in the different resistor and capacitor values to enable different pulsing speed. But here's the thing. There are a gazillion different optional variations to keep track of, and each A relay has slightly different wiring depending on the variations in each other relay and each other part of the circuit. So just doing this one part of the larger circuit was a whole entire week of work. The way it's expressed on the wiring diagram only makes sense after solving a huge multidimensional truth table, and even then, the poor quality of the original schematic left us wondering if this was a comma, a period, or a splotch of ink, each of which would have a different meaning. If this all sounds exasperating, it was. Matt and I spread this project out over several weeks and agreed to quit each day once either of us was feeling tired. There were some days where I went home and was just totally wiped out. We knew that there was nearly 100% chance that mistakes were made, but we continued on hoping that the mistakes would become plainly apparent once the circuit was actually fully constructed, and then it would be possible to actually troubleshoot and arrive at a conclusion. When they did this at the Western Electric factory, they had a few conveniences that we didn't have here. First of all, they weren't using these schematics to actually build the wire forms. They had running lists that told the workers which wires to lay down, in which order from start to finish. So the people wiring in the factory didn't have to care about the electrical details of the circuit itself. They just had to neatly put the correct wires in the correct places according to the list. Secondly, they had spools of every possible wire that they needed within arm's reach. We had to pull each wire out of scrap that I saved over the years, and if we didn't have any of the correct color, we had to substitute another one without it interfering with other colors also shared in that run. Sometimes we had to dig pretty deep into the scrap bin before finding a color that we needed, and that slowed us down quite a bit. But we did eventually finish running all of the leads, and it was now time to sew up the form. If you've never sewed a wire form before, you might not expect that it's such a physically intensive task, but it is. This is the sort of thing where you just have to jump up on the table and put your back into it. The wax twine is sewed in a chain stitch of sorts that binds all of the individual wires together into a single unit. Once it's done, it should be very stiff and able to mostly stand up on its own. And I actually enjoy this part of the project. This is the time when I can really just focus on the arts and crafts aspect without worrying too much about the math and electricity behind things. When we got back from Japan, I mounted the circuit in the frame and cleaned off the terminals of all the reused relays. I also gathered some terminal blocks and re-stamped them with the new designations for this circuit. Most of the wires that go to the A relays end up cross-connected on this wire wrap block here, so I'd better be sure that I've gotten everything right or there will certainly be weird failures. And now there's nothing left to do but start soldering the wire form. With the help of our volunteer Mac, I attached it to the framework and held it up temporarily. Eventually, it'll be held in place by the wires themselves, but for now, I'll need to keep it attached to something in order to fight gravity. After that, I went through and skinned all of the conductors. Oh boy, did my hand hurt after that. It was really brutal work to skin 400 or so wires at once, but it had to be done. And then it was soldering time. This part was just coloring by numbers. Look at the wire on the diagram and put that color on the correct terminal. That took 3 days overall, so I'll save you the boredom of watching me do that. Now that the main circuit is all wired together, it looks really nice, and I'm proud of how it came out. But before we can wire it up to the sender test frame, I have to do one more thing. Remember those A relays that cut resistors and capacitors in and out of the circuit? The way that they made this variable was to bring the contacts of those relays out to this cross-connection terminal block thing here. So to make this circuit work for the particular relays that I have here, I need to connect the correct values of resistors and caps into the contacts of the A relay. That way, when a particular A relay operates for a particular pulsing speed, I will actually get that speed and not something else. Now, I don't have the records for our panel switch, and even if I did, we are not in the same electrical environment. We are not using the same exact office battery voltage, and I am not using the exact same relays, so those cross connections wouldn't work anyway. This is one of those things that I just have to figure out myself by trial and error. So I got out the pulse counter and oscilloscope and started making connections with alligator clips until things started to make sense. Okay, that's 7 minimum, 7 max, 15 min, 15 max, 26 min, and then 26 max. 26 max. Cool. But seriously, the problems that I had, amazingly, they weren't terrible. Here's the list. And it's actually not that hard to just read it off. And bear in mind, I didn't find all of these at one time. This was the result of a week or two of working on the circuit, and I didn't film that because most of it is just me staring at a diagram and scratching my head, so don't worry, you didn't actually miss out on much. But we had cross terminals on the back of the A relays. That wasn't surprising since the terminals are all really densely packed. I put a wire in a wrong place on 2 different relays, just had to move them over one terminal. I forgot a ground on one terminal. I accidentally strapped together 2 capacitors that should not have been connected. I had 1 bad resistor that was open that I had to replace, 1 cap that was slightly out of spec, which is not bad for a single capacitor that's 80 years old. And I had forgotten 1 single wire in the wire form, and after double checking, I saw that Matt noted that wire on the schematic and that I would have to add it later, and I just forgot to double check that 1 note that he left. So I want to stress that this is incredible. We literally built a circuit from scratch, and the only real problems with it were really minor, easy things to fix. There were no fundamental logic errors or huge mistakes that cost us hours and hours of time. So that is awesome. Okay, so now I can finally wire it into the sender test frame. And this is as easy as running a cable up into the tray to the other side of the aisle and laying everything down on terminal blocks in the frame. I had filmed that, but then the GoPro died, so sadly you don't get to see it. After the circuit was wired, though, I had to make some modifications to the sender test frame to revert some changes they made to it in the early 70s. These changes would have explicitly stopped my circuit from working, and the 1970s modifications were explicitly things that I do not want in the test frame, so out they go. Then I got to work burnishing all of the relays in the test frame because they haven't moved in 40 years, so their contacts are a little crusty. And I used my special Western Electric burnisher for this, and it works great. So after fixing those little minor things in the test frame, it miraculously worked. So rather than me sitting here talking about it, just let's check out this video of us using the frame. Okay, so let's test some senders. Normally what this is going to do is it's going to iterate over all senders. So if we have 100 of them, it'll test all 100. I can have it repeat sender indefinitely or repeat twice, which is good to make sure that the thing that passed actually passed and it wasn't just a fluke. So I'll set up a number to call here. So I'm going to have the sender, or I'm going to pretend to dial 365 1234 into the sender. And then I also have to specify what I expect the sender to do. So for that, we're going to go district brush 2, district group 1, office brush O, office group 5, talk select O. I've got to select compensating resistance, and this selects what kind of test. There's different things you can test. And everything else looks good, so and it's dialing, and then it's reverted pulsing out, and the interrupters are going over there. So simulate those dial pulses and reverted pulses. And it's just going to iterate over every sender. So it finishes this test, it'll advance to the next sender, and it'll run the same test on the next one. And we have 6 senders, so it'll, in this condition, it will do this test 6 times. Unless I operate the repeat key, then it will stick to the same sender over and over again and just repeat the same test. I can operate this key, it'll show me lamps up here as the reverted pulses come in. They come in so fast that it barely lights the lamps at all. So that's a reverted pulse test with it dialing in here and then simultaneously up here reverted pulsing in. And it tells me what selection it's making and then what the numerical value of that selection is. So selection, numerical value of the selection. Okay, now on this test, we're doing something a little different. I've entered in some different codes here. And this is testing something called panel call indicator. It's a different type of language that the sender can speak to manual operators. Now this test is kind of like different because it's not reverted pulsing out. In this case, I'm keying in a number, the sender's accepting that number, and then it waits for a moment for the operator to come in and assign the trunk to herself. And then once it gets the assignment from the operator, it pulses out the number I've dialed using a totally different language that I should probably really do a video on, because I bet you'd find it interesting. So now we're waiting for assignment again, and then boop, 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 boop. So this thing is really working well. Like, I can do all sorts of different tests on the sender, and I can let it run on any sender forever. And even within like the first 15 minutes of using this, it found like serious problems with the sender that I would have never been able to find just by looking at it with my eyeballs, because this is able to perform tests in such a way that it could test things at the outside of the envelope and time individual milliseconds to see, like, is this relay really operating within the expected characteristic? If I'm sitting there dialing a telephone and watching the sender as I'm dialing, I just can't do the same thing that this is doing, which is timing stuff really accurately and with like accurate electrical characteristics and everything. So this is great. The other cool thing I can do now, and in order to demonstrate this, I have to go back to a different test. So 3, 6, 5. Okay, do that. Okay, let's go back to this test. And so I'm going to intentionally set up an error because I want to show you what happens if the test actually stops and there's a problem with the sender. So this, pressing this here, this test will never pass. There will always be an error, but let's just assume for you and me that there is this error is the result of some problem with this sender that now I have to go look at it. Well, I'm going about my business, maybe ignoring what the test frame is doing. So I'm going about my business, working on stuff, whatever, and the test frame encounters an error and it's unable to proceed. Well, it indicates that to me by illuminating that yellow lamp up there. This is at the end of the aisle. Normally there would also be a bell, but I've purposely not hooked up the bell because, well, I don't really need the bell to be going off. It's annoying, it's distracting to visitors, it's distracting to me, and like here in the museum, I will hook up the bell eventually, but life will go on. If the test frame encounters an error, I don't need to drop what I'm doing and go address the alarm. But I do have the visuals hooked up. That yellow lamp is on, indicating a test frame time alarm. There's a green lamp right there on the desk that's indicating a sender time alarm. So there's two things in alarm right now. There's the test frame that's in alarm, and the sender itself under test is in alarm. And this blinking light is telling me which sender it is. And it's sender A, B, C. So if we go over to sender C, open the cabinet and watch the actual sender under test. And I can use this tool. This is called a remote control. And the orange button, which they call red, but it's really orange. The orange button repeats the test. So I can watch this, and then I can observe where it failed. And then using the red button, I can repeat this test infinitely, and I could use my tools or whatever else to figure out what's actually going wrong in here that's making that test fail. And this is really nice too, because this takes all of the effort away from having to sit here with a phone and, dial a number. I can just hit this button and this test will repeat infinitely. It's like up arrow enter, basically. This makes it so much easier to fix things now than it used to be when I had to stand here manually dialing into these things. And because senders are so important and so complicated, it's really nice to be able to diagnose them. So I'm super happy. I'm super proud of myself for finally getting around to this project that I've been putting off for so long. And I'm super pleased that not only does the test frame now work, but that it actually found and is continuing to find real issues like adjustment problems and dirty relays problems that I would have not been able to ever notice, or that it would have taken me hours to locate manually by just going through every relay and the schematic and figuring things out. So it is awesome. I'm so glad I got this done, and now I can sleep easily at night and go off to do other things in the museum. So thanks for sticking with me through the video, and we'll see you next time. Bye.